Okay, so I welcome you once again to today's lesson. So we're going to begin looking at catalysis. So today we are going to deal with the first part of this topic, and then we'll finish up on Saturday. So this is the introduction. We are going to touch on various aspects. So I would like you to pay much attention because usually the introduction is very important to the understanding of the later part. So let's all participate and let's be together. So we are looking at catalysis. Catalysis. So the objectives that we need to know is that we're going to have an overview of metabolism. We're going to also have an overview of chemical reactions. We're going to also look at what enzymes are. We're going to look at properties of enzymes. We're going to look at structures of enzymes, or the structure of enzymes. We're also going to look at the regulation of enzymatic activities. We're going to look at inhibition of enzymes. And then we are going to look at also the factors that affect enzymatic reactions, or reactions that involve enzymes. So our framework of discussion of the outline will be as follows. So today we're going to have an overview of energy and reactions, an overview of energy and reactions. Then we are going to look at properties of enzymes, We're going to look at structure of enzymes. We're going to look at enzyme catalysis. We're going to look at enzyme inhibition and regulation. And we're going to look at enzyme helpers. So for today, we are going to cover energy and reactions, properties of enzymes, structure of enzymes, and if time allows, we're also going to touch a bit about, we are going to finish enzyme catalysis. I think we're just going to touch first part of that. So basically, this is how we are going to move. Now, what is catalysis? Guys, what is catalysis? Someone has an answer. What is catalysis? Or is it the first time we are hearing the word catalysis?
Yes.
How about the word catalyst?
Speeds up a chemical reaction.
Okay.
Without being changed.
Okay, thank you very much.
So I think catalysis is the acceleration of a chemical reaction by a catalyst.
Thank you very much. Yes, that's correct. Thank you very much. So simply, yes, the process of speeding up, increasing the rate of reaction using a catalyst. That's catalysis. And that's the main topic for our discussion today and on Saturday. So our concentration basically will be biological catalyst. So there are various catalysts that exist. So there could be non-biological and also biological. So we're going to concentrate on biological catalyst in our case, because we are looking at biology. So now, I'm sure we've heard of the word energy I think we've learned energy in physics, right?
Yes.
Yes.
Yes, we have.
Yes. What is energy?
In physics, it's ability to do work. Now, I don't know how you can define it in biology.
Okay, thank you. So it's a capacity or ability to do work. Of importance is that when scientists or biologists consider energy in chemical reactions, they often use the term free energy to describe the amount of energy that is available to do work. So free energy, it's the amount of energy that is available to do work. So if a reaction is supposed to take place, this free energy need to be available, and that's when the reaction will take place. So free energy. So energy is simply the capacity to do work. What are the two types of energy that exist that we know of? Of course, there are various types of energy now, the basic two types of energy that we know of. Because of energy transformation, energy is able to transform into other energies, but there are two types of energy that exist, which are
kinetic energy and potential energy.
Thank you very much. So we have kinetic energy and potential energy. Kinetic energy and potential energy. So what's kinetic energy? I think this is revision.
Energy in motion,
Okay, and potential energy,
stored energy.
stored energy. Yeah, so kinetic energy is energy of motion. So there are different types of kinetic energy, could be thermal energy. So there are quite different types of kinetic energy. Our potential energy is the energy which is stored, as he has mentioned, it is associated with position and configuration. So in molecules, this is referred to as chemical energy and is stored in the position of electrons. So kinetic energy is energy in motion. Potential energy is stored energy. It has potential, and that's called potential energy. It has potential, can be transformed. Actually, potential energy can be transformed into kinetic energy, isn't it?
Yes.
Like what example can you give?
A rolling ball, as in when it's on the ground, it has got full potential energy, but the moment it starts rolling, it will attain kinetic energy, and then the potential energy will lessen.
Okay. Now, during that process, for example, during that process, what happens to the total energy? Is it lost? Is it conserved? Or it is gained?
It is conserved.
Okay, so energy is conserved, right? So this is what we are talking about. You can have potential energy at the top of the waterfall, or you can have, for example, a stone or a ball at the top of the roof of the house. So that water molecule that is sitting at the top of the waterfall has a defined amount of potential energy. So as that molecule begins to fall, find that some of this stored energy is able to be converted into the energy of motion, which is kinetic energy. Now, as the rock drops and strikes, or rather as the water molecule strikes the rocks below, its energy of motion, kinetic energy, is converted to thermal it's also converted to mechanical, and also you can actually hear the sound that, okay, water is dropping, isn't it? So it's converted to sound energy. So we find that, remember I said that this potential energy is called potential because that it really has that potential. So this, what happens down at the waterfall there, we find that the potential energy is now much lower than it was at the top of the waterfall. Hence, we see that the change that has occurred in the potential energy has really been transformed into an equal amount of other forms of kinetic energy. In short, we are saying that this energy is neither created nor destroyed, simply changes form. So we are saying that energy undergoes transformations. Energy undergoes transformations. And during the whole process of transformation, the total amount of energy in the system will remain constant. So this is energy ability to do work. So Gibbs, we mentioned free energy, which is Gibbs free energy. Gibbs free energy. Someone last week actually asked about why the process of protein, was it last week or on Sunday? Last week. Someone asked why the process of protein folding is spontaneous. And I did mention that the process which is spontaneous has a negative Gibbs free energy, has a negative Gibbs free energy. And so for us to determine whether a chemical reaction is spontaneous or non-spontaneous, it is thus necessary that we assess all the combined contributions of changes in heat and disorder. So especially you're going to learn more about this when you, in your chemistry course, you're going to learn more about Gibbs free energy change when you start looking at the topic that deals with this. So in chemistry, you're going to learn more about that. So remember, the energy, free energy, the energy available to do work, the energy available to do work. Now, when a reaction, so a reaction can either be exothermic if it releases energy, exothermic if it releases energy, and then it can be endothermic if heat energy is taken up during the reaction. If heat energy is taken up during a reaction, that means that there is gain of energy, and that process or reaction is endothermic. So it has gained energy. So it generates an exothermic reaction will generate product which will have less potential energy than the reactants. Remember, the reactants are reacting, and in the process of the reaction, heat energy is given out, which means that the products will have a much lower potential energy. However, in the endothermic reaction, you find that heat energy will be taken up during the reaction, and hence the generated products will have a much higher potential energy than the reactants. So endothermic and exothermic reactions. Now, as we have already mentioned, that chemical reactions are spontaneous when Gibbs free energy is less than 0. So such reactions are said to be exogonic. Then those that are non-spontaneous are those with Gibbs energy that is positive or greater than 0. And these are referred to endogonic, as we have mentioned earlier. So when Gibbs energy is equal to 0, the reactions are in equilibrium. So you have exogonic less than 0, endogonic greater than 0, spontaneous less than 0, non-spontaneous greater than 0. So free energy will change when the potential energy of the substance changes. Free energy will change when the potential energy of the substance changes. So you need to mark that point because it will become also critical when you start looking at specifically the enzymes. So the free energy will change when the potential energy changes. So for a spontaneous reaction, it will run in the direction that lowers the free energy of the system. Remember, free energies, they are variable, the energy available to do work. The energy available to do work. So for a reaction to be spontaneous, it is going to run in the direction which lowers the free energy of the system. However, exogonic, as in the previous slide, exogonic reactions are hence spontaneous and also release energy. Endogonic reactions are non-spontaneous and will require an input of energy for them to be able to proceed. So there's an input of energy. It's not spontaneous. It needs input of energy for that reaction to take place. So no wonder it's called non-spontaneous reaction. This is a summary of what happens in a reaction. This will also become critical when we start looking at enzymes, because we are going to see what enzymes do. What enzymes do during this process or during this reaction. Okay. So we have the free energy here, and we have the progress of the reaction. We have the reactants A and B. Reactant A and reactant BC, well, reactant A and reactant BC. This is the progress of the reaction. And then we have the product of A, B, and C. So this diagram is simply showing the changes in free energy which occurs over the course of this reaction. So this is just a hypothetical reaction between molecule A and molecule BC. So when we are writing the reaction, we're going to write it as A plus B gives us A plus BC gives us A, B plus C. So remember, this is Gibbs free energy. This is Gibbs free energy. And then we have what is called the activation energy. The activation energy. So this is the energy which is required to make these reactants or the substrate or the substances, these reactants, to be able to react. It is the energy required for these substances to react. That's the activation energy. So that's the activation energy here, the EA. Okay, and then, so just remember this diagram. And we're going to explain more when we look at enzyme catalysis. So this is still showing the exogonic reaction and the endogonic reaction. So endogonic is gain of free energy, exogonic is loss of free energy. So remember I said that in exogonic, the product will have a much lower energy, while the reactants have a much higher free energy, because in this process, energy is given out, so no wonder the product have a lower free energy. And then for the endogonic reaction, the products will have much higher energy. So there's increase in free energy in endogonic reaction. Now, having talked about reactions, having talked about chemical reactions, having looked at how the reaction proceeds, I hope you still remember. You look at metabolism. Metabolism. So simply metabolism is a sum of all the chemical activities taking place in an organism. It is the total of the totality of the chemical reactions, of the chemical activities that take place in an organism. In an organism. That's metabolism. So we know that in an organism, for example, in human beings, for example, in myself here, there are a lot of chemical reactions that enables me to be able to conduct and carry out my activities. So for me to grow, for me to move, for me to maintain and repair myself, these chemical reactions are needed. And so when we combine all these and put all these together, it is what we call metabolism. Is that clear?
Yes.
Yes,
Okay.
sir.
Now, there are two main types of metabolism. When you look at an organism's metabolism, it consists of many intersecting series of chemical reactions. So it consists of many intersecting series of chemical reactions or pathways. There could be chemical reactions or there could be pathways. So it's either the reaction is anabolic or anabolism, or it is catabolism. Catabolism. So when you look at anabolism, this simply includes the pathways or the reactions for which complex molecules are synthesized from simpler substances. Anabolism is synthesis of complex molecules from simpler substances. What example can you give on anabolism? Guys, from our previous classes.
Building up macromolecules. Yeah, macromolecules.
Thank you very much. So an example of anabolism could be the linking of amino acids to form proteins, which was just our previous lesson. So that process of amino acid linkage leading to the formation of proteins is what we call, it's an example of what we call anabolism. Catabolism, this includes the pathways, the chemical pathways, the chemical reactions in which larger molecules are actually broken down into smaller ones. What example can you give, guys? Catabolism, guys. So I have an example, for example, hydrolysis or degradation of starch to form monosaccharides. When starch is degraded to form monosaccharides. In this case, glucose. So these changes that we see, these changes, these anabolic, catabolic reactions, will actually alter the arrangement of atoms and also various energy transformations. Now, when you look at catabolism and anabolism, there could be complementary processes. So sometimes we find that catabolic pathways involve an overall release of energy, some of which of this energy that is released would be able to power anabolic pathways. Remember, the anabolic pathways has an overall energy requirement. Now, those chain reaction, the chain of reaction that take place are what are called the pathways. Remember, I've mentioned about metabolic pathways. Those are the pathways. So that's metabolism. Now, what are enzymes?
Biological catalysts that are protein in nature.
Okay, thank you. Any other view? Or any addition? Anyone? What are enzymes? Okay, so that's correct. Thank you very much. So they are biological catalysts. So they speed up the chemical reaction, but remains unchanged in itself. They speed up the chemical reaction and remain unchanged. What is the name of the substances or the chemical on which enzymes react on?
Substrate.
Okay, substrates. Any other counter view? Okay, so that's correct. So the enzymes that are worked on, or rather the substances that are worked on, or that are being catalyzed are called the substrate. So what are some of the properties of enzymes? So we've already mentioned that enzymes are biological catalysts. Now, and he did mention that proteins, so most of these are proteinous in nature. So they are proteins in nature, most of them. And hence they exhibit all the properties of a protein that we looked at previously. So they're going to exhibit all the properties of the protein that we looked at previously. Of course, we have a few minor exceptions. Some RNA molecules recently have been discovered that they're also able to act as catalysts. So, but for us, we're going to concentrate more on the proteins. So they are protein in nature. The other one, since they are proteins, they are coded by DNA. They are coded by DNA. So from DNA to RNA to amino acids, linkages, so transcription, translation, and there's formation of these proteins or enzymes. Then there are biological catalysts, so they speed up a reaction. And then the enzymes are not used up, and hence they remain unchanged at the end of the reaction. So they remain unchanged, they're not used up. And then they do not change the result of the reaction. If starch is supposed to be degraded, the degradation of starch, what would be the result of the hydrolysis of starch? As hydrolysis of starch?
Is it glucose?
Yes, that's a complete hydrolysis. Yes, so during that reaction, remember from starch to give us maltose units, and then it's going to give us maltose, and then maltose will be converted to glucose. Now we have enzymes that react or that are involved rather during that reaction. Now, by that, we mean that even if the reaction, if the reaction there's no, if there's no enzyme taking, if there were no enzyme, for example, of course, enzymes take place in that reaction. But given an example, hypothetically, that there was no enzyme involved in the reaction, the result will still be the same. Glucose would be given out during the complete hydrolysis of starch. When we add, hypothetically, we add the enzyme, and then that enzyme catalyzes the conversion of starch, or the reaction which converts starch. The end result will still be glucose, still be the same. So they don't change the result of the reaction. This just speeds it up. And then we found that these enzymes are very efficient. They're very efficient. I want to give a try what we mean that they're very efficient. Efficiency. So when you look at the catalytic action that takes place, we find that a small quantity of an enzyme, or rather small quantities of enzymes, are actually sufficient. Even if where this quantity of enzyme is much smaller, when we compare it to its substrate. So you're saying that even if the quantity of the enzymes could be small, however, due to the efficiency of the enzymes, they're able to catalyze and produce a lot of substrates. So they are efficient. They are very efficient. So a small amount can produce more big amount of substrate. So small amount of catalyst produces big amount of substrate. That's what it simply means, very efficient. Is it clear so far?
Yes, sir.
Okay, thank you. So they are very efficient. What other properties do enzymes exhibit? So enzymes are very highly specific, both in the reaction that they catalyze and also in the choice of their reactants, in the choice of the substrate that they catalyze or the substrate that is involved. They are very highly specific. They're very highly specific. A protease, an enzyme that catalyzes a protein metabolism, for example, during the process of digestion, will not act on a carbohydrate. It is specific for a protein. A lipase, which acts on a lipid, will act on a lipid and not on a protein or a carbohydrate. So it's highly specific in its reaction. The reactions that these enzymes perform are reversible. So they can go in either direction. They are reversible. So forward and backward reaction. And then the other properties that enzymes are actually affected, and as we are going to look at these factors later, they are affected by various factors. For example, the pH, the potential hydrogen, the alkalinity and acidity. Yeah, so they're affected by the pH. Can also be affected by the temperature, and the activities or the reactions can also be affected by the enzyme concentration. So the activity is affected by various factors. So depending on the pH, depending on the temperature, these factors are going to affect the way the reaction is going to take place. So temperature will affect an enzyme, and we're going to look at this in our next lesson, how these affect the enzyme. And then they typically help change one form of energy. They typically help change one form of energy. And usually they help to form into a usable form. So for example, I can give an example of plants. Plants use a variety of enzymes to be able to capture energy that is stored in light. Remember, light energy from the sunlight, and convert this into a more usable form. That is into an energy that is stored in chemical bonds, for example, glucose. So we're talking about the process of photosynthesis. When we look at, for example, in animals, some of the energy that is stored in the chemical bonds, remember I said that those chemical bonds of glucose is able to be transformed, is transformed in the energy that is stored in the mitochondrial membrane. And then we find that this energy is able to be transformed into chemical bonds of ATP. Remember ATP? So I find that enzymes are very important in that they help change one form of energy into another, into a more usable energy. Do energy work alone? Typically, they do not act alone. They require what are called helper molecules. Okay. So since it's already 40 minutes, we can just log out and then we'll continue from here. Log out and we can log in.